All right, we're going to take a look at chapter 18 today using version 2 of the review document. And I've got 23 questions highlighted, so I think we can cover them in a couple of hours without too much difficulty. All right, number 1. For the reaction of sodium bromide with chlorine gas, sodium bromide with chlorine gas. It doesn't say the conditions of sodium bromide, whether it's in solution or not. So we just have to take it as is. And to form sodium chloride as a product, but those are solids. And bromine. Right? So you got two diatomics here, and you got two ionic compounds. So what's the question? The appropriate half reactions. Okay. So let's see. We got an oxidation and a reduction reaction we got to look at. And first thing we need to do is oxidation states, right? Elements, 0, 0. Ionic compound, alkali metals, +1. Halogens, that makes that a -1, +1, -1. Okay, so what kind of changes did we get? Oxidation is loss. Who lost electrons? Let's see. Sodium, nothing happened to sodium. It's a spectator. Bromine went from a minus to a 0. It lost electrons. So we got bromine. I think that's the way the answers are constructed. Yeah, with individual ions. So we're counting sodium as a spectator. And it's not entering into the oxidation or reduction steps. And that yields there. Okay. So how many electrons per bromine did we lose? Well, we lost 1 electron per bromine, but there are 2 of them, right? So that means we need 2 here and 2 here. So that leaves chlorine. Well, chlorine's going to be Cl-. And this, let's see, do they have states? No, we didn't include states here. So this adds an electron, but we need 2 of them. Okay. All right. So those should be our half reactions. Oxidation should be the bromide. 2 bromides yields 2 electrons and 1 bromine. That's B. B looks like a good candidate if the reduction is okay. So let's look at the reduction. Reduction, 2 chlorines, 2 electrons. See, 1 chlorine molecule, 2 electrons and 2 chlorides. That's it. So B should be the correct answer for that one. Okay. Take them in order for a few minutes here. All right. Ammonium metavanadate reacts with sulfur dioxide in acidic solution as follows. All right, so we have VO3 minus, VO minus. So that tells me that ammonium is a spectator. And SO2, right, yields VO2 plus. And sulfate. Right. And the coefficients are given as Y, X, Y, X. What that tells me is that this These two have the same coefficients. And these two have the same coefficients. So the ratio of X to Y would just be X divided by Y, whatever it happens to be. All right, how do we get there? Well, if this is an acidic solution and we have oxygens there, we need to separate them into their half reactions. So oxidation, let's see. We've got a -2 for each oxygen, times 3 is a -6, but we have to hold out one of them. So we only have to balance a -5. That makes this a +5. And -2 for each oxygen, -4 total. This is neutral. So this sulfur has to be a +4. That's a -2. Now we need +2 over here. So what would you add to a -2 to make a +2? A +4, right? +4 and a -2 is a +2. And here we have -2, -8 total. Keep 2 of them out. So this is a +6. So far, so good. Usually this one is the one that spins my students' heads around. Trying to figure that one out. Okay, so now we got the oxidation states. We can tell which one's oxidized, which one lost, which one went more positive. Vanadium went from +5 to +4. That's a reduction. So we know that VO3 minus has a +5 here, and it goes to VO2, VO with a 2+ here, and that vanadium is a +4. We had to add 1 electron here. I'm just going to put it in since we're already here. Now the oxidation is SO2 +4 for that sulfur, and we're going to sulfate with a +6. So we lost 2 electrons for each sulfur. And we may have to change those electrons once we get things balanced. But 1 vanadium and 1 vanadium, we're okay with that one so far. 1 sulfur and 1 sulfur, we're okay with that one so far. Now we got to balance oxygens. Okay. So we've got 4 oxygens on that side and 2 on this side. That means we need 2 more on this side. So we're going to make our oxygens with water. Right? So we need 2 oxygens plus 2 oxygens is 4 oxygens. But we've added 4 hydrogens. So now we have to put 4 hydrogens on this side to balance it. We've got 3 oxygens here and only 1 there, so we need 2 more. 2 oxygens there, we got 4 hydrogens here, 4 H pluses. Okay, now we need to balance electrons. We've got 2 electrons here, we need 2 here. Right? So everything has to be multiplied by 2. So that puts a 2 here, a 2 there, an 8 there, 2 here, and a 4 there. We use that up. Okay. Now we can bring everything together. Well, we can cancel some things, right? We can cancel the electrons. And we've got 8 hydrogens here and 4 there. So those 4 are out, and we're left with only 4 here. Waters, we got 2 there and 4 there. So these go out, and we're left with 2 there. Okay, so let's bring everything down. 2 VO3 minus, and then takes care of, takes care of this one. And then plus 1 SO2 plus 4 H plus. We can stop right here actually because we want the ratio of X to Y is 2 to 1. You can complete it just to be sure you did your math right. 2 VO2 plus and two, let's see. SO4 2 minus two waters. So yeah, X to Y, 2 to 1, 2 to 1. So the ratio is 2 to 1. All right. Okay, let's scroll to 3. Might get 4 in there too. 3. All right. Following reaction occurs in aqueous acid solution. In the balanced equation, the coefficient of water is. We're starting with NO3 minus. NO3 minus. Plus, let's see, I can read it here better. Iodide. And iodate ion. And nitrogen dioxide. Okay. If it says the question is, what's the coefficient of water? You can check to see, are we going to need water? Yeah, there's oxygen all over the place. So we are going to have water. If the question, say if I got tricky and said, what's the coefficient of water? And I gave you an equation where there are no oxygens, then you know that there's no coefficient for water because there are no oxygens there. Let's see. I guess if there were hydrogens there, we might, if it's acidic solution, that might necessitate a balanced equation. Anyway, we need two equations. And let's see, this is -2 for each oxygen, -6. We only have to balance a -5 to hold one of them out for that. So this is a +5. And there's a -1. There's a -2, -6 total. -5 +5 there. And a -2 times 2 is a -4. This is a +4. All right, now we can decide oxidation. Who lost? Nitrogen went from +5 to +4. It gained. So we might as well put it down here while we're here. Yeah, it's +5. And this is going to NO2 +4. And oxidation would have to be iodide to iodate. So this is 3 minus, this is a +5, and that's a -1. Okay, so we got one iodine here on either side, one nitrogen on each side. We're good there. Oxygens. We need to add 3 oxygens on this side. So 3 waters. That gives us 6 hydrogens on that side. We've got 1 too many oxygen on this side, so we need 1 on that side, which means we have 2 hydrogens on this side. Okay. Now we need to balance the electrons. We went from a -1 to a +5. That means we lost 6. We lost 1 to go to 0, and then we lost 5 more to go to +5. So we had 6 electrons lost. They always go on the product side. We gained just 1 on this side to go from +5 to +4. Okay. Now we can balance electrons. 6 electrons there, we need 6 here. So I need a 6, a 12, 6. Do better than that. 6, 6, and a 6 here. Now we can add them together. Actually, to answer the question, what's the coefficient of water? So let's bring the waters down, or do the waters. All right, we got 3 waters here, 6 waters there. Those go out. That leaves us with 3. So the coefficient of water is 3. Save yourself some time. All right, number 4. Following reaction occurs in basic solution. All right, we got waters and we got oxygen, so all right, we're gonna have to balance it that way. When the equation is balanced, the sum of the coefficients is. So we're starting off with fluorine and water yields oxygen and fluoride ion. All right, oxidation, reduction. This is a 0, that's a -2, and that's a +1. That's a 0, and that's a -1. Okay, so fluoride went from 0 to -1, it was reduced. And it went to fluoride. So it had to gain 1 electron for each fluorine. Oh, let's get the oxidation up here first. Excuse me. H2O went to O2, 0. So the hydrogens didn't do anything, but the oxygen did. It lost 2 electrons for each oxygen. So let's balance the fluorines. We need 2 here. We don't have any non-hydrogen, non-oxygen there, so we leave that alone for now. How about, well, we're not going to leave it alone because we got to go back to it. We got 2 oxygens here. We need 2 here, right? So that gives us 4 hydrogens. Okay. We don't have any oxygens here. We don't have any hydrogens here. So that was good. Now we can do electrons. With this oxygen, we went from -2 to 0, which means we lost 2 electrons for each oxygen. But there are 2 oxygens. So 2 times 2 is 4. We lost 4 electrons. 2 electrons for each oxygen. There are 2 of them, so that's 4 electrons. And then for this one, we had to gain 1 electron for each fluorine, but there are 2 fluorines, so we gain 2 electrons. Now, if we multiply this whole thing through by 2, we'll get 4 electrons to balance those 4 electrons. So we got 2 there, 4 there, and a 4 here. Right. And this is going to be in basic solution, I believe. Yep. So we're going to do the fake acid method. So we have 2 fluorines. We have 4 electrons that cancel out. We have 2 water. We have 1 oxygen. And we have 4 fluorides and 4 hydrogens. Let's see, did I bring everything down? Yep. Okay, so that's acidic solution. We can't reduce this any further because that's 1. Right, so we can't divide it through by a whole number and reduce the ratio. So now we want to get rid of the hydrogens. That means we have to add 4 hydroxyls on both sides. Okay, this gives us 4 waters. And that's 4 hydroxyls. So that cancels out these 2 waters, and now leaves us with 2 waters on that side and 4 hydroxyls. So the question was, what's the sum of the coefficients? We got 2 plus 4 plus, don't forget the 1, plus 4, and those are gone, and we're left with 2. So 2, let's see, 8, 10, 12, 13. Right. So D should be the answer. All right. Scroll. Number 7. Number 7, for the redox reaction, 2Fe2 plus CO2 yields 2Fe3 plus 2Cl minus. Which of the following are the correct half reactions? Okay. So let's start with, it looks to me like this is a balanced equation and they just want us to separate them out into halves. Chlorine molecule, 2Fe3 plus, and 2Cl. Right, so we can check it, like 2 chlorines, 2 irons. Okay. So oxidation, reduction. So this is 0, and well, that's convenient. All charges. All right, so which one was oxidized? Iron. So we have 2Fe2 plus yields 2Fe3 plus. 1 electron for each iron was lost, but there are 2 of them. And then we have the chlorine. Went from 0 to 2Cl minus. It had to gain 1 electron for each chlorine. So that's 2 electrons. Now, notice that, let's see. We can't reduce this one any further because that's a 1. But we can divide this one by 2. Right? So that's a 1, that's a 1, that's a 1. So the oxidation half reaction, the one with iron, let's see. The one with iron would be Fe2 plus yields Fe3 plus an electron. So that's Roman numeral 4. And the one with chlorine and 2 electrons yields 2 chlorides is Roman numeral 1. So that combination, 1 and 4, is A. Okay. Moving on. Scroll to number 8. How many electrons are transferred in the following reaction? All right. Number 8. I can read it better from here. 2ClO3 minus plus 12 hydrogens plus 10 iodides, 5 iodine plus chlorine plus 6 waters. All right. So in this one, we just want to tally. It looks like it's balanced. We can check ourselves, like 6, 6 oxygens on each side, 12 hydrogens, yep, and 10, yeah, it's balanced. So oxidation states, we got to find out which ones moved which way. -2 times 3 is -6, hold 1 out, -5, this is +5. That's a +1, that's a -1, this is a 0, this is a 0, and this is a -2 of the +1. Okay. So if we go, I'm going to draw tie lines for this one. If we go from this chlorine to this chlorine, what happened? It gained 5 electrons for each chlorine. Gained 5 electrons for each chlorine times how many chlorines? 2. Right? So 10 electrons were gained. Let's see if that matches with this one, because this is the only one that changed. It went from a -1 to a 0, so it had to lose. So we had a loss of 1 electron per iodine times 10 iodines equals 10 electrons. So 10 moles of electrons moved. Okay. Sometimes it's more convenient to do the tie lines than it is to half reactions. All right. number, scroll, number 11. All right. Consider a galvanic cell based on this reaction. Fe2 plus, Fe2 plus, it's dichromate, isn't it? Yeah. 2O7 minus yields Fe3 plus Cr3 plus. In acidic solution, calculate the voltage of the standard cell carrying out this reaction. The standard voltage. Okay, we've got a half reaction here of 2 plus to 3 plus, so that's your oxidation. We're going from Fe2 plus to Fe3 plus, your oxidation, and your reduction is the dichromate minus to the chromium 3 plus. So this one's easy. We lost 1 electron for each ion. We have to calculate the chromium for this one. -2 for each oxygen, -14 total, hold 2 out. -12 is the only one we have to balance, but we got 2 chromiums. So if we balance a +12 charge, each one of these is +6. All right. Now it means we gained 3 electrons for each chromium, but there are 2 chromiums. So we gained 6 electrons. All right. In order to calculate the standard voltage, we need to know what the half cells are, so we can look up their standard voltages. This one's not going to change it. Right. And remember, these are for standard voltages. These are intensive properties. So that's as far as we need to go. We don't have to balance electrons. We just need to know what is the standard voltage for this transition. Right. But this one, we might need to know something about the other components. Like this one's got 7 oxygens, so we need 7 waters over here. That means 14 hydrogens. Okay. So this is the half reaction we'd be looking for in the standard reduction potentials, which means I've got to scroll down to find them. Unless, well, maybe I can just look them up in the hard copy. Okay, so if we got Fe2 to Fe3, let's see. That's not it. And that's not it. It's over here somewhere. Here it is. Fe3 to Fe2 is 0.77. But that's for the reduction. This is reduction, right? This is oxidation. So we just changed the sign, right? Right. Negative. This is reduction. So we're going to look up the one that has dichromate on the left-hand side. And let's see if I can scan quick enough here. Dichromate plus 14 hydrogens and 6 electrons. Yep. Yields 7 waters. And 2. Okay, there it is. 1.33 volts. And that's a plus. 1.33 volts. Since these are already set up as this is the cathode, right? The site of reduction. This is the anode, the site of oxidation. So if we want to know the voltage, now we can just add them together. So that would be 7 from 13 is 6. 7 from 12 is 5. 0.56 volts, right? That would be D. Good. No protests. I assume we're good to go to the next one. That was number 11. All right, scroll. Number 14. A strip of copper is placed in 1 molar solution of copper nitrate, and a strip of silver is placed in a 1 molar solution of silver nitrate. 2 metal strips are connected to a voltmeter by wires, and a salt bridge connects the solution. Following standard reduction potentials apply. Okay. So we've got one cell reduction, standard reduction for one cell is, let's see, erase that. Read it from the board. Silver solid. So there's your solid silver strip. And this is standard potential is plus 0.80 volts. And then the other cell, we're not sure which one is the anode, which one's the cathode yet. This has 2 electrons. Yields copper solid. And this reduction potential is 0.34. Oops. Doesn't look like a 3. There we go. All right. So which of the following statements is false? I suspect we're going to need to know which one's the anode, which one's the cathode. So let's say which one needs to have be flipped in order to give us a positive voltage. If we flip this one to negative, that gives us a negative voltage, right? Negative 0.8 and plus 0.3 would give us negative. So this one has to be flipped. So it would be copper yields copper plus 2 electrons. And it would have a negative 0.34 volts. So we're going to add this one together with this one. And that gives us 6 and 3 is 4. Plus 0.46 volts. With this one as the anode, it's the oxidation side, anode, and this one's the cathode. Okay. So, so that we don't get confused, let's just draw that one out. There we go. Okay, now questions. Electron flow in the external circuit from the flows from the copper electrode to the silver electrode. Yes, if we have an anode on this side with the copper electrode and the cathode on this side with the silver electrode, then the electrons are going to flow that direction. Like that. And then we have our salt bridge. Okay, so A is true. We got the electrons flowing in the correct direction. How about B? The silver electrode increases in mass as the cell operates. Yes, because on this side, we're taking silver ions from solution and depositing them as a solid on the electrode. So B is also true. Mass is increasing on the cathode side. There's a net general movement of silver ions through the salt bridge to the copper half cell. No, you're not going to move silver ions that way because they're moving toward the electrode. You will get no migration of silver this way. Silver is moving that way under the electromotive force. Right, so this one's false. Right. If they're all unique, then you can stop there. Like if you're in the middle of a test and you need to get through it quick, you found the right answer. So D and E must be true. Negative ions pass through the salt bridge from the silver half cell to the copper half cell. Yeah, you're removing positives from here, so you got to get rid of the negatives. So the nitrates move this way, and the silver ions move that way. So D is true. And E should also be true. Some positive copper ions pass through the salt bridge from the copper half cell to the silver. Yeah. If we're removing solids this way and putting negatives back this way, then positives are moving that way, and negatives are actually negatives are being positives are being added to the solution. So we're getting an excess of positives, so the positive copper ions are going to move that direction. All right. That takes care of 14. 15. Hey. Which of the following species cannot function as an oxidizing agent? Oxidizing agent is reduced. The oxidizing agent causes the oxidation of something else, and in order to do that, it has to be reduced. So which one cannot function, cannot be reduced further? Well, let's see. How about sulfur? Yeah, right. It can go to a negative. It can be reduced. How about NO3? NO3 minus. Well, let's see. -2, -6, +5. It can be reduced further, right? It can go down to +3, 0. It can go down to even nitrogen, right? At 0. So that one would work. It can be reduced. How about dichromate? We did dichromate a little earlier. 2 minus. So this is a +6. Yeah. We can go down to +3. You know, the nasty chromium. Trivalent chromium is the bad one. So it would work. How about iodide? Can you add more electrons to that one? Nope. See, iodine already has its octet. When you add an electron, it's only deficient by 1. So add 1 electron. It's got a full complement. It's got its octet. That's the one that will not be reduced further voluntarily. And the MnO4, you use the same logic basically as this one. It can be further reduced. So your answer, the one that will not work, is iodide. All right. Oh, it's already up there. 16. Which metal, aluminum or nickel, could reduce zinc to zinc solid if placed in a zinc aqueous zinc 2+ solution? What we need, let's write these up here. So we have zinc 2+ and 2 electrons, zinc solid, and then aluminum 3+ plus 3 electrons yields aluminum solid, and then nickel 2+ plus 2 electrons is nickel solid. Okay. Now, if you were in working on your bachelor's in chemistry, they'd have you memorize the activity sequence so that you knew that which metal was more active than the other one, which means which metal is more likely to be oxidized, lose its electrons quicker. But for our purposes, I think it's more instructive to write these standard voltages -0.76 and then see which one gives us a positive total. Right? So we want to know which one could reduce zinc. Which one could make that happen? So that means this one has to be reversed and that one has to be reversed. right? Because these have to be oxidized in order to reduce that one. So we're going to leave this one alone, and we're going to say reverse this one and reverse this one. And then add each one together and see which one's positive. Right? If we add these two together, what do we get? Well, we get a positive, that's for sure. Right? 0.9. Positive 0.9 volts. So aluminum will reduce that zinc. How about nickel? Like 0.23 and minus 0.7. That's going to be 3 and a 5, but it's negative. So nickel will not do it. Nickel cannot. So only aluminum. That's it. Only aluminum will accomplish the reduction of zinc to zinc metal. All right. Might have to zoom in on this one after we find out what the question is. All right, consider the galvanic cell shown below. We have platinum on the left side, chromium on the right side, and the left side has a solution. When you see a platinum electrode, you can be pretty sure that the oxidation, well, if it's on the anode, if the oxidation will occur in solution and not involve the electrode itself. The electrode is just a conductor. So we've got bromine on the left-hand side being bromide being oxidized to bromine. And on the right-hand side, we have chromium 3 plus being reduced to chromium metal. All right. So what's the E for this cell? Well, let's look. Are those correct half reactions? Right. On the left-hand side, are we oxidizing? Well, let me see. What number is this? 17. Okay. On the left-hand side, we've got the bromine acting. And the standard reduction potential for bromine, this is a liquid, I think. Oh, no, it's in solution. Excuse me. Well, it has to be in solution. Otherwise, you won't get any reaction at all. And then this gives us bromide. So we need 2 of those. Okay. And the standard voltage is 1.090 plus 1.090 volts. Okay. But if it's on the left-hand side, by convention, this one should be oxidized. We should get this. And it should be a negative 1.090. And on the right-hand side, we've got chromium at Cr plus. I think this one's not going to work the way it's written. I think it's going to go backwards. Okay, well, let me finish putting this up here. Plus 3 electrons yields chromium metal. And that standard voltage is minus 0.727. All right. If we write these reactions the way they're shown in the picture, where this is the anode, oxidation, this is the cathode, reduction, we're going to get a negative value, right? So the way it's shown there in the picture is backwards. The electrons are actually going to go the other direction. And we're going to get this one is the cathode. And chromium solid yields chromium plus and aqueous. That's 3 electrons. This is the anode, and it's going to be plus 0.727 volts. Right. So to answer the question, what's the E0 for this cell? It's going to be this one plus this one. Right. Which should be, well, let me see, 7 and 11, 6, 8, plus 1.817 volts. A. Okay, that was tricky because the diagram was written backwards. I'm gonna leave that up there just in case we encounter it again. Let's see. Are we gonna see that one again? Let me just take a quick peek. There's a, that's a different. Number 17. That's 18.
No, that was 17.
No,
That was 17?
You just scroll to the next one.
Oh. Yeah, sorry. Okay. I'm just looking to see if save some writing if we have another one with those conditions. I think the next one is repeated several times, but this one is not. Oh, wait a minute. Are we going to do that one? Number 40. I hope it's highlighted. No, it's not. 40 uses the same situation, and it asks us what's the actual E for this cell at 25 degrees. So what would you need to determine the actual voltage for this cell? You'd need the balanced equation, right? The cell equation with these two. With these. Yeah, these two. Put together. Once you got the balanced equation, then you need the concentrations. And then you have to calculate the Q. And then the Q would go into the Nernst equation. And then you could calculate the actual voltage. But we're going to do that with a different equation, I'm pretty sure. We're going to use, yeah. Okay, so let's go back and pick up. No, that was not how. Okay, number 20. Yep, number 20. All right, so scroll back up. Ooh, no, wait a minute, I got 19. I got 18. Oh, 18. Let's see. 19 and 20. They're all based upon the same cell. And 21. That's 22 also. Those the same? Yeah. Okay. So we got one cell starting with 18, and we're going to work it through different scenarios. All right. So the value of E0 for this cell. So we got to see which direction does it flow? Is it written correctly? Do we have the anode on the left and the cathode on the right? you know what might help, rather than drawing out the diagram, is to do line notation. Right, we need to find out which one is correct. So if you got let me write those reactions down here first. MnO4 minus plus 8 hydrogens plus 5 electrons yields Mn2 plus 4 waters. And E0 for this one is 1.506 volts. And the other one, CR207, plus 14 hydrogens, plus 6 electrons, yields 2 CR3 plus 7 waters. And its standard reduction potential is 1.330 volts. Okay, so which one do we have to flip to get a positive voltage? This one right here, right? This one has to be the anode. So we got to write it so that it's the anode. 2 CR3 plus 7 waters yields CR207 2 minus plus 14 hydrogens plus 6 electrons. This will be a minus 1.3 volts. Okay, we can answer this question right now. All we have to do is take this one and add it with this one, and that'll give us the standard potential for this cell, which would be, let's see, 6, 7, 3, 1, 0.176. C. So C is correct for that one. Okay. All right. Now for the next one, we're going to take that same cell. Let's see, is it written correctly? It's written backwards, isn't it? Manganese is on the left, but it's the cathode. And this is the anode. All right, so that cell is written backwards from our standard format. All right, the question for this one is, when current is allowed to flow, which species is reduced? Which one is reduced? Okay. We're reducing MnO4 minus. So the answer to that one is C. Correct? All right. Now, what's next? What is the value of Q, the reaction quotient for this cell reaction? Okay, now what we have to do is combine this into a single equation. So we'll take this one and add it to that one. So we have MnO4 minus plus 2 Cr. Oops, getting ahead of myself. Can't combine them yet, can we? Because electrons don't match. So we gotta combine the electrons. See, we got 6 here and 5 there. Oh, how do you match those? Got an odd and an even. Remember the magic word? Cross multiply. Multiply this one times 6. And this one times 5. So we take that 6, multiply this one. We take that 5, multiply this one. So that gives us 6 here, 48 there, 30 there, 6 here, and 24 there. Okay. And this one is 5 times 2 gives us 10. And this one gives us 35. Right. This one gives us 5. This one gives us, what's 5 times 14? 70. And then this one gives us 30. 30 electrons. Okay. So 30 electrons move. 30 moles of electrons move. Now we can add them together and get our combined equation. Okay, so we have 6 MnO4 minus, and let's see, 10 Cr3 plus, and then 48 hydrogens and 35 waters. And on the product side, we get 6 MnN2 plus, and then 5 Cr2O7 minus, and then we get 24 water and 70 hydrogens. Okay. Now let's reduce this. Can't divide through by a whole number, so let's cancel some things. 48 hydrogens here, 70 hydrogens there. These hydrogens are gone. So what's left over? 22. Okay. Waters. 35 waters here, 24 there. So those waters are gone. Minus 24 is 11 waters. Okay. And I don't see a way we can reduce it, so that's where we are. This is our balanced equation. So we're going to calculate Q. All right, what's the concentrations of each of our components? MnO4 is 0.1 molar. Chromium 3 plus, 0.4 molar. Okay. Waters. Oh, water's a pure liquid, right? It's not part of the equation. We're talking equilibrium here. Manganese 2 plus, we're starting off with 0.20. 0.20 molar. Dichromate ions, 0.30 molar. And hydrogen ions, we got 0.01 molar. 0.01 molar. Okay, so the Q is going to be what? It's going to be Mn 2 plus to the 6th power. And dichromate to the 5th power. And hydrogen ions to the 22nd power. Okay, that's your products. Reactants. MnO4 minus to the 6th power. Chromium 3 plus to the 10th power. And that's it. Now we just need to put the values in. Now, just because we got big numbers here in the powers, don't go chasing cars, right? Just be methodical. This is the correct expression. Now we put our values in. Mn2 plus, 0.2 molar, 0.2 molar to the 6th power. Dichromate. Where's dichromate? 0.30. 0.30 to the 5th power. And hydrogen ions, 0.0. Let's do better than that. 0.1 molar to the 22nd power. Then divided by the manganate ion, 0.1 to the 6th power. And chromium 3 plus is 0.40 to the 10th power. Go. So now we just need to do some math. out our calculators. All right, 0.2 to the 6th power. And there it is. Okay, I'm going to change my display so I can see more decimals. Okay. And then 0.3 to the 5th power. And I'm going to multiply those two. And then 0.01 to the 22nd power. I'm going to multiply those. Okay. So on the top, I get 1.56 times 10 to the minus 51. And now on the bottom, 0.1, 6th power. And then 0.4 to the 10th power. Multiply those two. And in the denominator, I get 1.05 times 10 to the minus 10. And then divide those two. So overall, I get 1.48 times 10 to the minus 41. Or round it off. Actually, two significant figures is proper. 1.5 times 10 to the minus 41. Okay. That was a lot of work, I know. But we can use that value in the next problem, I think. Where we're going to take this same reaction. Oh no, we're going to do what is the coefficient of H plus? All right, here's our equation. H plus is 22. So that's D. We already got that one answered. And let's see, 22 wants to know what's the cell potential at 25 degrees. All right, so now we need the Nernst equation. We got 30 moles of electrons. The Nernst equation is the actual voltage equals the standard voltage minus, let's see, 0.691, is it? Remember the Nernst equation. That's why I put it in here. Nernst. Here it is. 0.591. I was thinking of something else. 0.591 over the number of moles times the log of Q, correct? All right. So now, let's see. Let's erase this part. Keep this. All right, so that's equal to standard voltage. What's our standard voltage? 176. 0.176 positive. Minus 0.0591 over 30 moles of electrons. Times the log of Q, which is I'm going to use 4.8. It'll probably be a little bit different if we use 1.5 times 10 to the minus 41. Okay. So take the log of that one first. It's already in my calculator, so I'm just going to hit the log button. So this value is minus 4.083 on my calculator. And times 0.0591 divided by 30. And this whole thing here is minus 8.04 times 10 to the minus 2. And then we're going to subtract that. So subtract a negative is a positive. So we're going to say 0.176. And I get 0.256 volts. All right. It says E 0.26 rounded off. Okay, there you go. That's the actual voltage you'll get out of that cell. So what did we do? We got more voltage than the standard. By choosing our concentrations. Or they were chosen for us. But never mind. Let's see. How about number 30? See how we doing? We're doing good. Got another hour if you need it.
Are we going to go over the lab today?
Yeah, we can a little bit if there's time. There's really not much need. We're just going to make a battery. It's kind of like follow the recipe. Okay. There are no pre-lab questions in it, are there? No.
I think it's
No.
just the questions.
Yeah, just questions at the end. Okay. All right. Number 30. The following has a potential of 0.92 volts. Let's see, mercury 2 plus hydrogen. Oh, okay. All right. I may not need to do this, but I'm going to do it anyway. We got 2Hg 2 plus hydrogen yields 2H plus aqueous plus Hg2 Hg2 2 plus. So which one's oxidized and which one's reduced? The mercury goes from what? It goes from 2 plus to actually 1 plus, right? Because there are two mercuries. Remember, that's the way mercury acts. It's funny. It's always two mercuries. Well, it's always a 2 plus charge. But if it's a 2 plus on a single mercury, it's a 2 plus oxidation state. If it's a 2 plus on a dimer, then it's 1 plus. So it went from a 2 plus to 1 plus. It was a loss, 1 electron per mercury times 2. So that means we had to gain electrons here. Gain, let's see, how many electrons? We went from a 0 to +1, so it gained 1 electron per hydrogen times 2 equals 2 electrons. Okay, so they're telling us that the potential for this cell is 0.92 volts. 0.92 volts is the potential for that cell as written, where mercury is oxidized. This is the anode. And this is the cathode. What is this? This is the standard hydrogen electrode. Right? So what's its voltage? By convention, 0 volts. Okay. So if this one, if we're oxidizing at this voltage, right, we get that voltage, but this is being oxidized, what would its reduction potential be since that one's 0? Its reduction potential would be minus 0.92. Correct? All right. So there's something wrong with this question. If the I didn't read the whole thing. If the concentration of the ions were 1 molar and the pressure 1 atmosphere for hydrogen, then E0 for the half reaction Wait a minute. I went the wrong direction. Didn't it? Yeah. We went from a 2 plus to a 1 plus. It gained an electron. Sorry. Let me back up. Well, that's still right, whether it's an anode or cathode. This had to gain an electron. Gain 1 electron for each mercury to go from a +2 to a +1. And that means this one would be a loss of 1 electron. Okay, this is still 0 volts. So if this is the loss, that means it's the anode. This is the cathode. So this gained electrons, and it's written correctly from left to right. Whatever voltage we get from this is the standard reduction potential for mercury. So that's why D is the answer. It's a plus 0.92. Simply because it's written as reduction. Reduced from here to here. Standard reduction potential against 0 hydrogen electrode. That's correct. I had it backwards. And nobody caught me. Don't feel bad. My students usually don't catch me with these mistakes. I try to catch them myself so that you don't go off thinking the wrong thing. All right. Next. Number 44. An excess of finely divided iron is stirred up in a solution of copper 2 plus ions, and the system is allowed to come to equilibrium. And so we got iron metal, right, and copper 2 plus ions. What's likely to happen? Well, if the copper is more active than the iron, no, iron would have to be more active than the copper, so that the iron would be oxidized. Then the potential is that we would go to, well, I don't know, it could be 2 plus or 3 plus. Let's say it's 2 plus for argument's sake, and this would be copper. And it's allowed to come to equilibrium, whatever that is. The solid materials then filtered off, and electrodes of solid copper and solid iron are inserted into the remaining solution. What potential developed between these 2 electrodes? All right, that's a little misleading, because if you've got both of them in the same solution and you put the 2 electrodes in there, well, if the solutions are the same, right, for both anode and cathode, then yeah, you would expect that this would be like a lead acid battery where you have the common solution. If that's the case, then when you put the electrodes in it, are you going to get a voltage? No, because it's at equilibrium, right? When you're at equilibrium, you don't get a voltage. You still have a standard potential, but that's based on 1 molar concentrations. Right? But if it's at equilibrium, you don't get a voltage. That's a trick question. The answer is 0. All right. How about 49? Let's see, you make a cell with an aluminum electrode in a solution of aluminum nitrate and a zinc electrode and a zinc nitrate. If you could increase the concentration of aluminum, which of the following is true about the cell potential? All right, so let's write this out. You got aluminum 3 plus. I'm going to write it as a reduction first. Aluminum 3 plus 3 electrons goes to aluminum metal. And then the other one is zinc. Yeah. The other one is zinc 2 plus 2 electrons goes to zinc metal. Okay. What would happen to the cell potential? Well, let's see, what's the cell potential going to be? Well, we don't have to deal with acid or base. What we need is standard potentials. That's right. Aluminum 3+ and zinc 2+. So let's go to our standard reduction potentials. And let's see. Aluminum 3+ is -166. This is standard. And then let's see, zinc 2+. There it is, yeah. 0.76 negative. Negative 0.76 volts. Okay, so which one's going which way? This one's going to be the anode. Because if we make this one positive, it won't help us any. Got to make that one positive. So now we're going to have aluminum yields, aluminum 3+ plus 3 electrons, and we get plus 1.66 volts. So under standard conditions, our voltage should be 0, almost a volt. Okay. So if we combine the equations, right, we've got 2 here and 3 there. That means we need 3, 6, and 3. We need 2, 2, and 6. So we'll write our equations: 2 aluminums plus 3 zincs yields 3+. 2 aluminum 3+ plus 3 zinc metals. Okay. And that's our standard voltage. So what are we going to do to it? Increase the concentration of aluminum 3+. Increase this one. Right? We increase that one, we're going to drive the reaction backwards and the voltage will decrease. Okay. Le Chatelier. We're working against the electromotive force by going that direction. So that's why the voltage would decrease. All right. 56. How many moles of electrons are produced from a current of 14.4 amps in 3.2 hours? Moles of electrons. Okay. Well, if we're going to run it for 3.2 hours, that's time, 3.2 hours. And the current, well, actually current is, the symbol for current is I. Capital I. The current is 14.4 amps. Right. Remember what I said amp was? It's 14.4 coulombs per second. Okay. So what we need is to find out how much charge has been transferred and then make the conversion from charge to electrons. So in 3.20 hours, how many seconds is that? How many seconds in an hour? That's minutes in an hour. 60 minutes in an hour, 60 seconds in a minute. Right. Okay, so we got that down to seconds. Now we want to convert that to charge. So our conversion factor here is 14.4 coulombs for every second. That gets rid of the seconds. Now we want to convert coulombs to moles of electrons. Moles of electrons, coulombs. Let's see, not, I forget the conversion factor.
96,000 for 30.
96,485. Yeah. 96,485 coulombs. And that should answer our question, right? How many moles of electrons? Well, if we do the math correctly, we should get 1.72 moles. Okay. Let's see. Who's next? Who's next? 64. Is that right? Okay. $64. What mass of chromium would be deposited by electrolysis of an aqueous solution of, chromium 2 sulfate? Not chromium 2 sulfate, chromium 3 sulfate for 145 minutes using a constant current of 11 amps. Okay. So if we're going from, we need to know the stoichiometry of this reaction. If we're going from a solution of chromium 3 sulfate, that, right? This is aqueous. And let's see, this is going to, well, what's the charge on that chromium? It's the coefficient of this one. It's 3 plus, because this is 2 minus. So cross. Are we going from chromium 3 plus? So actually, sulfate is a spectator. We can do this. Chromium 3 plus in an aqueous solution. Plus how many electrons? 3 electrons yields chromium metal. That's the equation we want right there. Okay, so how much charge is being transferred? Time is 145 minutes. 145 minutes. We need seconds, don't we? Minutes, seconds, so 60 seconds in a minute. Then we need the amperage, 11 amps. 11 coulombs per second. Okay. Now we need our conversion for moles of electrons. 96,485, was it? That'll give us moles of electrons. Now we need to convert moles of electrons to moles of chromium. So what's the ratio? For every 3 moles of electrons, we get a mole of chromium. Okay. And the question was mass, wasn't it? What mass? So now we need to convert moles of chromium to grams of chromium. 52, okay. There we go. So now it's just number crunching. Okay. Equal 17 grams. Okay. And got lots of different ones there. Oh, okay. 72. Balance the following equation in acidic solution. That looks familiar. Did we do that one already? Well, we got time to do it again. So we got dichromate plus iodide, ion, yields chromium 3 plus iodate. Right. In acidic solution. Okay, so we need to split it into oxidation and reduction. So this is +6, isn't it? We did that one before. That's a -1, 3. And this one is -2, -6, +5. Okay, oxidation. Which one was oxidized? Iodide. It went from -1 to +5. So iodide goes to iodate +5 -1. And that leaves dichromate. Went from +6 to Cr3 plus. Okay. So we got 2 chromiums here, we need 2 chromiums there, 1 iodine here and here, that's good. Now we'll balance the oxygens. We need 3 oxygens on this side. That. Now we need 6 hydrogens on this side. Okay. We have 7 oxygens here. We need 7 oxygens over here. Now we have 14 hydrogens. Okay, now we can do electrons. We went from a -1 to a +6. We lost 6 electrons for each iodine.
How many get 6?
We lost 1 to go to 0,
Oh,
and then 5 more to go to +5. So we had 6 electrons. On this side, we went from a +6 to a +3, but there are 2 of them. So we gained 3 electrons for each chromium, but we have 2 chromiums, so that's 6 electrons. Is that right? Yeah. Okay. We must have had a different reaction before, because I don't remember having this come out that nice.
no, we had a multiply. We had a cross multiply.
Yeah, so this is a different equation. Yep. Okay, and this is an acidic solution, so we can do some canceling here. 3 waters leaves 4 here. Electrons are gone. And let's see, hydrogen ions, we have 6 here, which means 8 on this side. So balance the equation. All right, so let's balance it. That's Cr2O7 2 minus plus iodide ion plus 8 hydrogens yields 2 chromium 3 plus iodate ion plus 4 waters. So that should be there. Correct. Okay. Balance the following equation. Bismuth hydroxide plus 10(2) oxide yields bismuth plus 10(3). This is a basic solution. Okay. We've done one of those, fake acid. We may not have to convert this one, because bismuth hydroxide is already a base. It may set us up for a basic solution after we cancel everything and bring it down. It might already be basic. So we're starting with, let's see, 75. We're starting with bismuth hydroxide. You ever swallowed bismuth before? How about Pepto-Bismol? Yep. Pepto-Bismol has bismuth subsalicylate in it.
Taste it chalky.
Probably. Yep. But it takes care of a couple of things. It's upset stomach, it's basic. Plus, it quiets your stomach because it has salicylates in it, not painkillers. And it stops diarrhea. All right. SNO2, SNO2, 2 minus. And then we're going to end up with bismuth metal. I don't think you want that in your system. SNO3. Right? Yep. All right. So, it looks to me like these are going to separate out. This is a +1, this is a -2, and this together is a -1. So we got 3 minuses, has to be balanced by 3 pluses. Okay. Oxygen, -2 times 4 is -4, but we're holding 2 of them out, so this is a +2. And this is a 0. -2 times 3 is -6, hold 2 out, -4, +4. Okay, now we have the oxidation states. We can split it up into oxidation and reduction. Okay, so if we're going from bismuth +3 to bismuth 0, it had to gain 3 electrons. Add 3 minuses, and you go to a neutral. So this is the reduction step. Bismuth hydroxide. And this is +3. This is +1, and this is -2, just in case. And we're going to bismuth zeros. Okay. Is that an aqueous solution? Doesn't say. It would have to be aqueous. So the hydroxyls are already in solution. Let me see how I approach that one. No, we're okay. All right, oxidation. SNO2 minus, this is a +2, and it's going to SNO3, 2 minus, +4. Okay. Bismuth, 1 on either side, 10, 1 on either side. This one has 2 oxygens here and 3 oxygens there. So we need another oxygen on this side. But that means we need 2 hydrogens over here. Okay. On this side, we have 3 oxygens. So we need 3 oxygens over here, right? Plus 3 waters gives us 3 oxygens. Now we got 6 hydrogens that need to be on this side, but we already got 3. Right, so we need 3 more, right? So 3 more hydrogens will balance that. Now electrons. This one's the oxidation step, so we're going to end up with, for each 10, we're going to end up with 2 free electrons over here. We went from +2 to +4, means we lost 2 negative charges. We went from +3 to 0, that means we gained 3 electrons for each bismuth. Okay, now we can cross multiply. We have 3 here and a 2 there. So this one is multiplied by 2, this one's by 3. All right, so now we have 3 here. We have 3 there. We have 6 here, 3 there, and 6 there. And we have 2 here. We have 6 here. We have 6 here. That's good. 2 here, and we have 6 here. Okay. So now, let's cancel some things. The electrons. Get rid of those. We got 6 hydrogens here, 6 hydrogens there. They're gone. And waters. We have 3 waters here and 6 there. So those waters are gone and we're left with 3 here. Now we can bring it down. So it won't look so messy. So we have 2 bismuth hydroxide. And then 3 10-2 oxide ion. Let's see. No more on this side. Okay, that's good. Now on this side, we have 2 bismuth element and 3 SN 2 minus plus 3 water. Okay. And that's basic because of those hydroxides right there. Now, I don't know how soluble bismuth hydroxide is, but from our experience, even if it's slightly soluble, it's going to be in excess of hydroxides and make it a basic solution. Just depends on the concentration as to how basic. So let's see. Does it agree with? Yep. That's the balanced equation in basic solution. Oh, we're done.